The other two tests that we are going to cover to finish out this section are both comparison tests. There are two of them. One of them is called direct comparison, and the other is called limit comparison. Comparison tests are usually the very last option I go to try to figure out if my series is convergent or divergent, because these really require you to already have an idea on whether your series converges or diverges. You really cannot go into a comparison test blindly and determine without any previous guessing or previous knowledge about your series whether it's going to converge or diverge. So with the direct comparison test, we're going to be given some series, and we're really not going to have a straightforward test of the ones that we've learned so far that we recognize that we could easily perform on it. So what we have to do is find another series to compare it to. And usually that series that you compare it to is something that follows one of the other tests very easily, and you know that it either converges or diverges. So if your A sub n's are always less than or equal to your B sub n's for some other series B sub n, and this other series B sub n, we know that it converges. Well, if all of the terms in your series are smaller than the B sub n's, and B sub n converges, that means your series must converge as well. So we really have to have an idea going into this of what exactly to compare it to, whether we think ours is convergent or divergent. That way we can compare it to an appropriate second series. If all of our A sub n's are greater than or equal to B sub n, and the sum of the B sub n's diverges, well, if all of our terms are larger than those and those diverge, then ours must diverge as well. So it's very important that you try to determine ahead of time whether or not you think the series you're given converges or diverges. That way we can figure out what to compare it to. So if we think that ours converges, then we need to find a series whose terms are larger. If we think that ours diverges, we need to find a series that has terms that are smaller than ours. And we'll look at a few examples where direct comparison is a good test to use. And usually the only reason we would come to that conclusion is because all the other tests are not good to use. And we can make a guess ahead of time of whether we think it converges or diverges. The first one we're going to look at is the sum from 1 to infinity of 1 over 3 to the n minus 2 to the n. This one, it would be very difficult to integrate. It is not a geometric series because there's two terms in the denominator. The limit is 0, so we can't use the divergence test. This one, everything is not raised to the nth power, one big nth power, so we can't do the root test. Also, the ratio test, because there is no distinct function of n in the top, the ratio test will also most likely come out inconclusive. But if you remember back, one of the very first tests we learned was the geometric series tests. And if you take either of those denominator terms individually, we could think of them as individual geometric series. And whether we set it up for the first one or the second one, Here we have a R value of 1/3, which means this is a convergent series. So most likely ours converges because of how similar it looks to a geometric series test, but we can't actually apply the geometric series test because of the subtraction in the denominator. So what I'm going to do is I'm going to compare it to a geometric series that uses just one of those terms. And we're going to call this one a sub n. Well, if I'm going to guess that it converges, then hopefully I will find that the terms of the b sub n are larger. Because if the b sub n terms are larger and they converge, then certainly our series that has smaller terms would also converge. So what we need to do is we need to write out some of the terms for each of these series to compare. So when n equals 1, we're going to have 3 minus 2, which is 1. When n equals 2, I'm going to have 9 minus 4 in the denominator, which is 1/5. When n equals 3, we're going to have 27 minus 8, which is 1/19. For b sub n, when n equals 1, we have 1/3. When n equals 2, we have 1/9. When n equals 3, we have 1/27. So we've run into a problem here. These a sub n terms are larger than the b sub n terms. So that doesn't really tell us anything in terms of convergence or divergence. Because if we think ours converges, then we've got to find a series whose terms are larger and it also converges. So look what we have to work with here. These are the terms from our series. We need to find something that converges and whose terms are larger. It is possible that they are allowed to be equal though. So what we just figured out really is that this one is really not going to be helpful at all. If we suspect that ours converges, then we need to find a series that converges and has larger terms. So we're dealing with 1, 1/5, 1/19. We need to come up with a series for b sub n whose terms are larger than that, but also converges. So the next one I'm going to try is 1 over n squared. I know that this is a convergent p-series because of the format it's written in. We've got a p-value of 2, and we said anytime p is greater than 1, the series would be convergent. And if we compare these values with ours, when you plug in 1, you're going to get 1. That's okay. They're allowed to be equal. When we plug in 2, we get 1/4. So we might be on the right track because 1/4 is bigger than 1/5. When I plug in 3, I get 1/9. Still doing great because 1/9 is greater than 1/19. And this is going to continue with squares in the bottom. I'm going to write a few more of the terms from a sub n out so that we can see if the trend continues here. So if we were to plug in 4 to our original series, 3 to the 4th is 81, 2 to the 4th is 16. So 81 minus 16 is 65. And I think right there is where this is going to go bad. So on the 4th term, ours is, oh no, that's still good. Ours is 1/65th. Theirs is 1/16th. Ours is much smaller. So that's actually exactly what we were looking for. And since I went out 6 terms there, I'm going to go out 6 terms here. If we plug 5 into our original series, we'll have 3 to the 5th minus 2 to the 5th in the denominator, which is 1 over 211. And our convergent p-series here is just 1/25th, so we're definitely smaller than that. And then I'm going to check real quick one more. It seems like our terms are getting smaller much quicker than this 1 over n squared p-series are, and that trend should continue. 3 to the 6th minus 2 to the 6th would be 1 over 665. So these terms definitely are far smaller than this convergent p-series. And that proves, since the a sub n's, when we compare these two, the a sub n's are definitely smaller than the b sub n's. And we know b sub n is convergent, so any series that has smaller terms would also be convergent. We're going to look at one more really quick, where we're going to try to use the direct comparison test. So this time, let's say we're trying to find the sum from 1 to infinity of n squared plus 2n plus 1 over 3n squared plus 1. There is another test that you could use to prove whether this is convergent or divergent, but just in case you don't recognize this, for almost all of the problems in this chapter, there are multiple tests that will work. There's only one correct answer in terms of convergence or divergence, but there's lots of ways to reach that conclusion. So direct comparison test is probably not the best test for this one, but just in case you don't recognize another test, we could use direct comparison. So let's look at some of these terms to get an idea of what's happening. If we plug in n equals 1, we're going to get 4 over 4, which is 1. If we plug in n equals 2, we're going to get 4 plus 1, which is 9, over 2 squared is 4 times 3, 12, 13, 9/13. If you plug in n equals 3, we're going to get 4/7. And if you plug in n equals 4, you're going to get 25 over 49. And this just keeps going forever. We know that in order for any series to converge, the terms have to go to 0 pretty quickly. And it looks like these terms are headed in that direction, but they are not moving very quickly. We're at the 4th term, and we've only gotten to about a half. So I'm going to guess that this thing diverges. And it's very important that you make that educated guess before you decide what you're going to compare it to. So there is a p-series, and this is what I'm going to guess for my b sub n, of the sum from 1 to infinity of 1 over n. So this is a p-series with p equal to 1. And anytime we said p is less than or equal to 1, it's divergent. So I found a series to compare it to. Now, in order to show that our series diverges, our values must be larger than the 1 over n values. So we've got some values written out for our a sub n when n equals 1, 2, 3, 4. Now let's write out some of the values for the b sub n. When n equals 1, we have 1. Okay, that's good because they're allowed to be equal. When n equals 2, we have a half. Well, 9/13 is larger than a half. When n equals 3, we have a third. 4/7 is definitely larger than a third. And when n equals 4, we have a quarter. 25 over 49 is definitely larger than a quarter. If you need to change these to decimals in order to compare them, then you should do that. But 25 over 49 is almost a half. It's a little over a half. And this divergent series by the 4th term is already at a quarter. And you could generate a few more terms here as well if you would like to. But it is apparent from these first 4 terms that the terms in the a sub n are always greater than or equal to terms in the b sub n. And our b sub n is divergent. So certainly any series who has terms larger than that would also be divergent. The second comparison test in this section is called the limit comparison test. This one has a much more concrete mathematical method to it, but it shares some resemblance with the direct comparison test in that you have to have an idea ahead of time as to whether you think your series is going to converge or diverge, and then be able to come up with some sort of series that looks similar to it. So the limit comparison test says that we'll be given some series that we're asked to determine the convergence or divergence of. We will need to find another series, b sub n, such that the limit as n approaches infinity for a sub n over b sub n we're able to calculate. And usually that requires those series to have similar types of functions inside them, or something like that. So this limit, depending on what that limit comes out to be, we can say for certain what the relationship between our a sub n series and our b sub n series. So we need our b sub n to look similar to a sub n so that this limit is not too difficult to calculate, but b sub n also needs to be something that we can easily determine the convergence or divergence for. So like a very straightforward divergence test problem, or geometric series, or p-series, or integral test problem. So there are several possible outcomes here, depending on the value of L. If L comes out to be something between 0 and infinity, exclusive, it can't actually equal 0 or go off to infinity, then the a sub n series and the b sub n series either converge or diverge together. That means if we know what b sub n is doing, we're guaranteed that a sub n is going to do the same thing. Our other two options here are if L actually equals 0 or infinity. So if L equals 0 and our sum for our b sub n's converges, then the sum for the a sub n also converges. That is only true for the 0 case. If L is equal to infinity and the sum for the b sub n's diverges, then the sum of our a sub n's also diverges. So we could not use option 2 here to prove divergence. If L goes to 0, it can't prove divergence. And likewise, we can't use option 3 here to prove convergence. So we try to stick with something that comes out to be between them when we calculate the limit. And that's why a similar looking series is required. So as long as that limit comes out to be something in between 0 and infinity, which is what's going to happen most of the time, then we're guaranteed that our two series do exactly the same thing. And number 2 and number 3 are just like special cases. The limit comparison test is nice for when it looks like we have a specific type of series, except there's just one part of it that's off. Like if we had a geometric series, and geometric series are a times r to the n. The only variable we see in those is in the exponent. So if there happened to be another variable in there somewhere, other than that it looked like a geometric series, then that might be a good example for using limit comparison. Or like a p-series where we typically see n to some power in the bottom. If we see n plus or minus a constant to some power, that might be good for the limit comparison as well. So the first one we're going to look at, the sum from 1 to infinity of 2 over n plus 3 squared. I want to know if that converges or diverges. And there's possibly a different test that we could do on this to determine that, but I just want to show you an example of how exactly the limit comparison test is applied. So this almost looks like a p-series. If that plus 3 wasn't in the denominator, then we could say that this is a p-series with p equal to 2, which is convergent. So what we're going to compare it to, we're going to call what they gave us the a sub n, and we're going to compare it to a typical old p-series that leaves off the extras. So I'm going to leave off that extra coefficient of 2 in the top, and I'm going to leave off the plus 3 in the bottom. Those look very similar, but I know, sorry, that should be squared, but I know what b sub n does. This is a p-series with p equal to 2, and we said anytime that p-value is greater than 1, it would converge. So we're guaranteed that a sub n will also converge if I can set up the limit between these two sequences of numbers here and get some finite answer, something between 0 and infinity. So we're going to calculate the limit as n approaches infinity of the a sub n, which is what we started with, over the b sub n, which is what we have decided to compare it to. So just like our ratio test, instead of dividing two fractions, we will flip and multiply. And this limit will probably be a little bit easier to recognize if we multiply these together and also expand them. So in the top, I've got 2n squared. In the bottom, I've got n squared plus 6n plus 9. Now the limit as n approaches infinity, because these are polynomials, they've got matching degrees, so the limit is the ratio of the leading coefficients. So this limit is 2. And that's perfect, because anytime we get a value between but not including 0 and infinity, that means the series that we chose is going to dictate what the original one does. So we chose a very simple convergent p-series. The limit came out to be some finite number. That means our series, a sub n, also converges. So b sub n converges. Therefore, a sub n also converges. We really don't care what this number comes out to be, as long as it's not 0 or infinity. If it's 0 or infinity, then we are limited, because remember, equal 0, we can only prove convergence. Equal infinity, we can only prove divergence. So we prefer it to come out something in between, then it could prove either one of them. One more quick example. We're going to try to determine if the sum from 1 to infinity of 3 over n times the square root of n plus 1 is convergent or divergent. So what we're given is a sub n. Well, we know 3 over n all by itself would be a divergent p-series, and any power of p bigger than 1 would be convergent. So it almost seems like the addition of this square root of n plus 1 is just enough to make this series teeter from divergent to convergent when we compare it to a p-series. So I'm going to pretend, I'm going to do a little bit of algebra rewriting here. So that n in the front is the same thing as the square root of n squared. And now that both factors in the bottom are under a square root, we could really combine them and say this is the square root of n cubed plus n squared. This series is identical to the first series. We just did a little bit of algebra rewriting to make the entire denominator look like one cohesive unit rather than two individual expressions. So this is hopefully going to help us figure out what to compare it to. Now, when I compare it to something, I want the limit to come out to be some finite number between 0 and infinity. So I'm going to compare it to the series of 1 over square root of n cubed. So I'm going to leave off the 3 and I'm going to leave off the n squared. And most likely these two series are going to do very similar things. They're going to have fairly similar values. As we go off to infinity, n cubed is going to have a much more substantial impact on the value for the series than the n squared will be. So this we could rewrite as 1 over n to the 3 halves. So that is a p-series with p equal to 3 halves. And because 3 halves is greater than 1, this is a convergent p-series. And if we can take the limit of a sub n over b sub n, and it comes out to be some finite number, that will be enough to prove that a sub n is also convergent. So we're going to calculate the limit as n approaches infinity. On the top, we're going to put the a sub n. And I'm going to put this algebra simplified version of it because I think the limit will be easier. In the bottom, I'm going to put my b sub n. Instead of dividing, I'll flip and multiply. So now we've got the limit as n approaches infinity. Well, part of my numerator and part of my denominator are both under a square root, so we could really combine them into one large square root. I've got 3 times the square root of n cubed over n cubed plus n squared. Now inside that square root we have a polynomial and the degrees match, which means we can use the coefficients to determine the limit of the square root part. So this is going to end up being 3 times the square root of 1, which is just 3. So we got a finite number answer, something between 0 and infinity, that's not equal to 0 infinity. And what that means is whatever b sub n is doing, we're guaranteed that our a sub n is going to do the same thing. So since b sub n was a fairly simple convergent p-series, this limit now proves that our original series a sub n is also convergent. Now, there is a one more test that is not in our book that's very, very useful, and it's really a combination between p-series and comparison series. And I've seen this in other calculus textbooks, and it's called the polynomial test. This is anytime you've got a sum of some rational expression, which means we've got polynomial in the top and a polynomial in the bottom. You could do a limit comparison test between this series and a p-series with similar exponents to determine convergence or divergence. But since it's going to be true every single time, we really could name our own test for this. So these are both polynomials. And whether this converges or diverges is based on the degree for P of n and Q of n. So let the degree for P of n equal big S. Let the degree for Q of n equal big T. In order for this to be convergent, we need the degree for Q of n, which we're calling T, to be at least 1 greater than the degree for P of n, which we've called S. So we need to make sure that T is greater than S plus 1. Or if you were to find the difference between them, that difference must be greater than 1. If you think about a p-series, just a very simple p-series, 1 over n, the difference in degree between the numerator and denominator is exactly 1, and that was divergent. But as soon as that difference goes above 1, it would be convergent. So something like this is divergent, and then something like this would be convergent. And if you just think about what the difference in those degrees are, both of the numerators here have degree 0. But when the denominator is degree 1, they have a difference of exactly 1. That is not enough of a difference for it to be convergent. That is divergent. But as soon as the power goes up to 2, now the difference is bigger than 1. It's 2. That means it's convergent. And the same is true even if these were very complicated polynomials. It's really only the leading term, the term with the biggest exponent, that's going to have the largest long-term impact on those values. And we probably could use this polynomial test on some of the ones that we've done earlier, now that we know it. Let's say we've got the sum from 1 to infinity of 3n squared minus 5n plus 2 all over n cubed plus 6n squared minus 1. Now we don't have to try to do any crazy integral tests, and we don't need to do the comparison tests either, which make us kind of have a guess ahead of time of what's happening. We can do the polynomial test on this since we've got a rational expression with a polynomial in the numerator and denominator, and we see the degree of our numerator, which we called S, is 2. The degree of our denominator, which we called T, is 3. And we need T to be greater than S plus 1. If you plug your numbers into this, T is 3, S is 2. Is 3 strictly greater than 2 plus 1? It's not. We need more than 1 unit difference between those in order for it to be convergent. So therefore, this one would be divergent, and we could simply justify this by saying the polynomial test. So this will make a lot of the problems a lot easier that look like they might be set up kind of like p-series, but much more complicated.